Hello everyone, welcome back to my channel FusiBots. In this video, we will going to learn how to find the analytical inverse kinematic solution for a 6 degree of freedom robot. In the previous videos, we learned how to make a URDF file for 6 degree of freedom robot. Then we have also learned how to do the forward kinematics of the robot. In that video, I have also told you about how to assign DH parameters and get the forward kinematics ready. Then we have also learned joint space trajectory planning. Now the next step is Cartesian space trajectory planning. For that we have to do inverse kinematics. So inverse kinematics can be done analytically or numerically. So today we are going to learn how to find the analytical solutions for inverse kinematics. So this is our robot. These on the left, these are the actual frames and these are the DH frames. We already know this. I have explained in my previous video. These are the DH parameters. So with the help of this DH parameters and forward kinematics, I get these three equations. So these are the three equations for XYZ coordinate with respect to base, and this is the wrist point, which is the wrist point. This is basically my wrist point, this one. Here this is my wrist point, this is my end effector point. So coordinates of this point with respect to this base are here XYZ. How to get these coordinates I will tell you later, but first just assume that we have coordinates x, y and z. Now how to solve these equations? So we know that we know x, y, z. What are the unknowns here? That are three unknowns: theta 1, theta 2 and theta 3. First of all, we have to understand how we can get to the inverse kinematics of 6 degree of freedom robot. So there are 6 variables. First, basically, what is inverse kinematics? It is basically we have end effector position. From this we have to find the joint angles. So there are 6 joint angles: theta 1, theta 2, theta 3, theta 4, theta 5 and theta 6. So these are the 6 angles I have to find. So for that I have to do decoupling. So how decoupling works? Basically, we know that out of this 6 degree of freedom, the position of end effector is basically affected by first 3 angles and orientation is affected by last 3 angles. So what we will do, we will decouple the effect of last 3 angles. How? Because we know that the position of point 5 is only affected by theta 1, theta 2 and theta 3. Theta 4, theta 5 and theta 6 cannot affect the position of this. So with the help of this, I get this type of orientation, where starting from here we go like this, and this is the wrist point. Now the position of this point is only affected by theta 1, theta 2 and theta 3, not by theta 4, theta 5, theta 6. With the help of this, we will first find theta 1, theta 2 and theta 3. And once we get these 3 theta, then finding theta 4, theta 5, theta 6 are very easy. So first of all, we have to understand that we have 8 solutions possible for 6 degree of freedom robot. Analytical solution. So how to find them? First we will take the equation number 1, that is x equals to this, and equation number 2. For example, this is equation number 1, this is equation number 2 and this is equation number 3. First we will find all these equations. I will multiply first with cos theta, second with sin theta and add it. After adding, you can see that these all are cancelled out and we will left with only this: x cos theta 1 plus y sin theta 1 equals to L6. And we already know, whenever we have this type of equation, a cos theta 1 plus b sin theta 1 equal to c, then we can easily solve this type of equations. How to solve them? We will just take a triangle like this. First I will divide by under root of x square plus y square to LHS and RHS. Then I have, for suppose we have this type of triangle whose perpendicular is x and base is y. So hypotenuse will be under root of x square plus y square, angle will be alpha. So from here, sin alpha will be x upon under root of x square plus y square. So here we have sin alpha or sin gamma, you can say. And then we have cos gamma, that is y upon under root of x square plus y square. So we will get, from here we know that cos a sin b plus sin a cos b will be sin of a plus b, and that is equal to c. So I have got sin of a plus b. Now cos of a plus b will be plus minus under root of 1 minus cos a, 1 minus c square, basically 1 minus c. So this is there. So then tan gamma plus theta 1 will be equal to c upon under root of plus minus 1 minus c square. So theta 1 will be tan inverse c upon this minus gamma. Okay, and what is this gamma actually? This gamma is actually this angle, this. So tan of gamma equals to x by y, that is perpendicular upon my base. So gamma is tan inverse x by y. So I can replace this gamma with tan inverse x by y. Similarly, for theta 2, what I have to do, I have to take equation number 3. This is my equation number 3. I have taken L1 to LHS. Z minus L1 will be equal to L3 cos theta 2 plus this. Now this cos theta 2 3 means, here 2 3 basically means theta 2 plus theta 3. So you know that theta cos theta 2 plus theta 3 is cos A cos B minus sin A sin B. So I have opened it. After opening, I have taken cos 2 theta common here, sin 2 theta common here. Again we get a equation like cos theta 2 plus y x means a sin theta plus b cos theta equals to c, something like that. But here you have to first understand that we must know theta 3, then only this whole become constant, but we don't know theta 3 till now. But let's suppose we know theta 3 for now. I will tell you how to find it. So if we get equation similarly as done above, we will solve for theta 2 also by solving this equation. Now the big question is how to find this theta 3. So this theta 3 can be easily get by the geometry of our robot. So we know that our robot, this is my L1, this is my, for example, L3 dash, and there is this L4, there is this L5, and there is L7. So this is how my robot is basically. Now I will apply cosine law to this triangle. And how this side, how I got this side. So actually there is an offset of L4 in my robot. I can show you that. So there is this offset. So how you can find it is, for example, we have some offset here L4 and we have this L3 dash, then we have this L3. So why we give this offset? So in our robot till now I have not given this offset, but generally we give this offset to avoid singularities. So I will explain you how it helps you to reduce the singularity. But first of all, let's understand, now we have this L3. So if there is no offset in your robot, then you can directly write L3 as L3, and if there is an offset in your robot, you can write L3 as L3 dash ka square plus L4 square. So that is the only difference, if you give offset or not at the elbow angle. So we apply cosine law with that L3 square plus L5 square minus x square. X is this length, you add by 2L3 L5, that is cos of 180 minus theta 3. Theta 3 is this one, that is angle between link 2 and link 3. Yeah. So cos of 180 minus theta in second quadrant, that is minus cos theta 3. Then how to find this x, how to find this distance? So we know that this is L1, that is 0 0 L1. This is the z axis, and we know the coordinate point of this x comma y comma z. So I can directly find Euclidean distance, x minus 0 ka whole square plus y minus 0 ka whole square plus z minus L1 ka whole square. With this I can easily find my cos theta 3 L5 square. Okay, so now this L3, if you have an offset, this L3 will become L3 dash ka square plus L4 square. If you don't have any offset, this is directly L3 square. So that depends on whether you have elbow offset or not. Then you have cos theta 3, you have sin theta 3, and you have tan theta 3, and I can find theta 3 equals to this. And why I am always using tan of theta 3? So that my solution will be between minus 180 degree to 180 degree. If I use arc tan inverse or a tan 2 in CPP library or any Python library, so that my solution will always be between minus 180 to 180. And depending on the range of your robot, for example, if your robot can rotate for complete 360 degree, then you can just add 2 pi to the solution if it crosses this solution. So that is also easy. So once I have theta 1, theta 2 and theta 3, I can easily find theta 4, theta 5 and theta 6. How to find this? I will explain you in a Python code. So now I will go to my Python code. I will explain you how I got these equation, and I will also explain you how I will get theta 4, theta 5 and theta 6 with theta 1, theta 2 and theta 3. I will give you a glimpse here how to do it. So with the help of theta 1, theta 2 and theta 3, what I will do, I can easily find my transformation matrix from base till third frame. And what I want, a transformation matrix from third to last sixth frame, that will be equal to 0 to 6. So this is the property of transformation matrix basically. So I know what is the matrix from base to wrist. So this is the matrix from base to wrist. This matrix I know easily because now I know theta 1, theta 2, theta 3. So this is also known matrix. Now I have to find this matrix only. This is unknown. So can I find it? Yes. T36 is basically T30 ka inverse multiplied by T06. And once I get T36, I can easily know what are my theta 4, theta 5 and theta 6. How? I can just represent my symbolic representation of theta 4, theta 5, theta 6. When I have a symbolic representation of my matrix, I can directly compare it with the numerical representation. This is numerical representation, this is symbolic representation. And I can directly find what are my theta 5, theta 4 and theta 6. So in this way I can do it. So now I will move to the Python code. We will see how we got those three equations in Python. So basically I have made a transform symbolic function using the simple library of Python. With the help of this, these are defined according to my DH parameter that I already explained you. Now this is a ZYX transformation matrix that is defined, that already I explained in my forward kinematics video, but in this I have made it as a symbolic matrix. With the help of this symbolic matrix, I will find it for a range of n. For example, for a range of 6, these are for all 6 joints. So after applying this, and if I display this matrix, I will get this equation. So this is basically the wrist transformation matrix. So first starting column 3 by 3 matrix is the rotation matrix, and this last one, this one is the translation of the vector. So this is x, y and z coordinates, and this is 1. So basically you know this is a homogeneous transformation matrix. From this I got those equations. I solved this equation to get the analytical solutions. Now the next question is, how can I get my theta 4, theta 5 and theta 6? For getting theta 4, theta 5 and theta 6, we have to move forward. As I already told you, now we know what is my transformation matrix for T03, as I have theta 1, theta 2, theta 3. I know what is my matrix from T0 to 6. So how can I get my T3 to 6 matrix, that is T03 inverse into T06, and if I substitute some values here, I will get the numerical value of those the numeric matrix. So this is basically my symbolic matrix, symbolic transformation matrix from frame 3 to frame 6. You can see that there is a cos theta 5 here, sin theta 5 cos theta 4, minus sin theta 4 sin theta 5, sin theta 5 cos theta 6, sin theta 5 sin theta 6. From here we can easily find theta 4, theta 5, theta 6. We can just compare it with the matrix with the numerical values that we already find. We can directly compare this cos theta 5 with that value. We will get cos theta 5 from here. Then after comparing this with that value, we can directly find theta 4, and by comparing this with that value we can find theta 6. In this manner we can find theta 4, theta 5 and theta 6. Now we have complete solution of theta 1, theta 2, theta 3, theta 4, theta 5 and theta 6. So we can say that now we have the inverse kinematics, like complete inverse kinematics. So this is from my side how we can find an analytical solution for the inverse kinematics of 6 degree of freedom robot. In the next video we will implement it for doing the Cartesian planning. So in Cartesian planning we will use these equations. We will find all the solutions for each of the Cartesian point and we will select a solution from it. So in the next video I will explain that if I am getting an 8 solution for each of the point, then how can I manage of choosing the solution. Like my solution can be anything, because we know that inverse function is not a one-to-one map, it is one-to-many map. So for one anti-factor position we have 8 pair of joint angles basically, which can correspond to the same end effector position. But how can I choose that? So in the next video we will do Cartesian planning and we will understand that. So stay tuned for that. Thank you for watching the video. If you like the video, subscribe to our channel Fuse Robots for more such videos.